The aim of today's lecture is to explain the Braess paradox and to introduce the emergency stage simulation model in sim events. Well, first of all, the Braess paradox was introduced by Braess in 1968 under the title of his contribution, that is about the paradox of traffic planning. So the Braess paradox is about traffic. Let's go to the main idea that's behind this paradox, this statement. The main idea is that improving something can make it worse. So when you give a process more resources, it is not forced to imply that the system will improve the performance. Okay, that's the idea. When you give more resources to a process, its behavior, its performance is not forced to improve. So let's go to this example. This is a traffic example, okay? So cars want to go from A to D. This is the origin, and this is the target node, okay? And we have two different ways to reach node D, that is the destination, the target, okay? You have this route, A, B, D, but you have also A, C, D. As you can see here, we have some formulas that depend on X. X is the traffic load. Okay, so the number of cars in this route, in this section of the route. So that's the idea. X is the number of cars, the number of lorries or whatever, or buses, okay, within this route, within this section, okay? So if we have one single car, the time it takes to go from A to B is 5 multiplied by 1 plus 1. So it's 6. For a single car to go from A to B, it takes 6 minutes. 5 multiplied by 1 car plus 1. So 6 minutes. So the resulting number of this operation is number of minutes it takes to go from A to B. And the same goes from B to D. X is the traffic load, again. So for one single car, it takes 1 plus 25, 26 minutes to go from A to D by means of this B node, by means of this waypoint. Let's have a look at the alternative route that is here. Here we have A to C. For a single car, it's 1 plus 25, it's 26, the same as this. And here we have 5 multiplied by 1 plus 1, it's 6. So again, here we have 26 plus 6 is 32 minutes. Okay, that's the idea. So for one single car, we have the same time from A to D if we take the upper route or the lower route. Okay, that's the idea. So it makes no difference to take ABD, ACD. If we have two cars, one car can go through this and the other one can take, for example, this. And both have the same time for this route, for ABD and ACD. But what it happens if we have, for example, 6 cars, 6 commuters, okay? Because the main idea is that the original example from Braess is about traffic, about traffic jams, about traffic planning, okay? But this can be applied to electrical circuits, to water supply nets, and the like, okay? So it's not only about traffic. It can be applied on dynamic systems in general. So if we have 6 commuters, then the time it takes, let's say that here we have 6 multiplied by 3 plus 26. This formula is about the following. As you can see, the time it takes to go from A to D is 5x plus x is 6x multiplied, plus 26. Can you see here? Because the time it takes to go from here to the destination is 5x plus x, 6x plus 26, okay? And the same, it goes from A to D, but going through the C node, okay? So if we had 6 commuters, 3 commuters through this route and 3 commuters through this route. So we have 6 multiplied by x, that is the total load, the traffic load through this route, and the total load through this route. 3 cars per route. That's the main idea. So it takes 44 minutes. Okay, fine. So in order to improve this traffic planning, the proposal is the following: to have a link, a bidirectional link, as you can see here, a bidirectional link that is only 1 minute cost. Okay, so the total cost for this link is only 1 minute. Let's suppose that we have many different lanes for every direction, because this BC is bidirectional. So you can go from B to C or from C to D. You can go in either direction, okay? So the original situation is as follows. For 6 commuters, remember, it takes 44 minutes through this route or the alternative route. Let's check what is happening with this new link, with this new resource in this traffic planning, okay? So for the first traveler, the best route is obviously A, B, C, D. A, B, C, and D. This goes for the first traveler. If you have only 1 commuter, the commuter will go through this, this, and this. Why? Because the total cost is 10x, as you can see, 10x plus 3. Okay? So then you have here the total time of 30 minutes, because it's 10 plus 3, okay? Well, what about the second? The second will follow the same route. Why? Because of the selfish behavior of drivers. If you have a route that is so short in time, you will prefer this route as an alternative through the original one or the alternative one. And as you can see, if you take the other one, x plus 25 here, and x plus 25, if you go through this route, it's about 2x, but you have a basis of 51 minutes, okay? So this route is not a good option, okay? So let's go again for the second commuter, the second traveler, okay? He or she will follow the same route that the first traveler followed before, with a time of 23 minutes. Why? Because now the total traffic load is 2. So here you have 10, 11, 12, and 11, it's 23 minutes. Okay, that's the idea. And then the third and the fourth will go like the two previous, okay, because this is shorter, okay, and the times they will spend in the road, in this route, will be 33 and 43, okay. As you can see here, we are close to the original time, 44 minutes, okay. But then the fifth and the sixth commuters, the fifth and the sixth travelers, the best routes are now ABD, ABD, or ACD, the original ones. Okay? Why? Because as you can see, we had reached the limit just before the original route that was without this new link. So the conclusion is that if you add a new resource, it is not forced to imply an improvement of the traffic planning. So this extra speed, high-speed route was an improvement only for the initial travelers, for the initial commuters. But the overall effect has been to slow the network down by nearly 20%. Because then, for the fifth and the sixth drivers, the travelers, they will take a total time of 52 minutes. Why? Because here we have, as you can see, 5 and 6 traffic loads. As you can see, X for the fifth and the sixth, X in this section will be 5 multiplied by 5 or by 6, okay? That's the idea. And then if you go through this, it will be, for example, 26 in here for the fifth driver, okay? It will be 26 here, and then here will be 26 again. Why? Because here X is equal to 6 or to 5. X is equal to 5 in here, okay? But here, a single driver is going from B to D because the 4 first drivers are going through this route, remember? But for the fifth driver, this route is not optimal. The optimal route will be this, okay? So that's why here there are 5 travelers, but here X is equal to 1. So we have a 26 minutes route. So the total time is 26 plus 26, this 52, okay? And again, for the sixth traveler, we'll go through this alternative. And it goes the same, 26 in here, because only the sixth driver is going through this route. But here, X will be again equal to 5, because the first 4 drivers go through this, and the fifth is following this route, okay? So the main idea is that then it worsens the total time for every route. So that's the general idea. If you add a new resource, it doesn't imply to improve the performance of the system. But the Braess paradox has several different traffic plannings where it can be applied. For example, if we had to go from A to B, here we have a bridge that lower down the speed, okay, and also the capacity for drivers through this bridge. And the same goes for bridge 2. Let's figure that here we have a river, okay? We have a river, and we have this route and this different route, but both have a bridge. because a river is going through these two routes. Okay, so the same situation happens in here. The increment in here is similar to have different speeds in different sections for the same route. Okay, and the final message is that there is no need for the network to be symmetrical. Here, remember that we had symmetrical. This value is the same than this, and this is the same than this. But the message is that the Braess paradox can be applied to non-symmetrical plannings, okay? Here, as you can see, we have some symmetrical situations, but these are far from symmetrical, okay? That's the idea. Well, so the conclusion is that if you add new resources to a system, it doesn't mean that the situation will improve, okay? So we will apply this in order to plan how doctors will assist patients in the emergency stage of a hospital, okay? So the lab work for today's lecture is to build a model about the incoming patients at the emergency room of a hospital, okay? So the general idea is that you have the resources. The resources will be split in two different classes, okay? First of all, we have nurses, okay? And then we have doctors, okay? Nurses will be in charge of the triage section, while doctors will be in charge of the doctor care, okay? So resources will be of two different types, yeah? And within doctors, you will have different colored doctors. It's only a kind of classification, okay? When you get to the emergency stage of a hospital, doctors are classified into different areas, into different severity of illness, okay? That's the main idea. We will see it later. So first of all, we have the patient arrivals, okay? It will depend on the day of the week and on the time they arrive. It's different, late at night, early in the morning, in the middle of the day, okay? So it will be different depending on the time, on the simulation time at the end, okay? First of all, patients will reach the triage section. This section is in charge to classify the patients, okay? It's different if you had a earache, okay? It's different if you had, for example, if you had broken a leg, if you had cut your arm. So depending on the severity of your illness, you will be classified into different colors, okay? There will be a color code for the patient classification. And obviously, depending on the color code you are assigned, then the doctor will be in some, you will be assisted for different doctor areas, okay? That's the general idea. Well, first of all, what about this color code I referred in the previous slide? Well, I had taken this from a renowned contribution, okay? It's about some time ago, but it's like the general flow chart about how a patient is being classified, okay? First of all, the first question and the main question, is the patient dying? Yes. So the level is assigned to be immediate, okay? Surgery and the like. That's the main idea, okay? Is the patient dying? So yes, level 1, the highest severity of illness, okay? No. So then, should treatment begin immediately? For example, if you had broken an arm, if you had broken a leg. So, for example, like traumatology could be level 2 very urgent assistance. Okay, that's the idea. No, so you should not have a treatment so immediately. Okay, so how many resources do healthcare professionals have? Known, one, many, depending then on the resources, you will be classified on urgent, standard, or non-urgent. Okay, that's the general idea. So level one means highest severity of the illness. Five means that it's the lowest severity of the illness. That's the main idea. And these color codes, I had extracted these color codes from the Manchester triad scale levels, okay, the Manchester Hospital. Well, this is a well-known from you about how can you deal with the working shifts in a simulation model, okay? You have here the clock time. Remember, the stop time in this model will be 24 hours, 60 minutes per hour, 7 days a week. Okay, so we will simulate the whole week in minutes. Okay, in minutes. Fine. So how can we get the shift number? Every shift is 12 hours long, 60 minutes. So the shift length in minutes is this. So you divide these minutes by the total length of a shift in minutes. Then remember the numbers here, you will have 14 shifts, okay? So really this number will go from 0, passing through 1, 2, 3, and the last number will be 13, okay? 13, this will be the last. Then we floor this this number, and then we add 1 in order to have from 1 to 14. Okay, that's the total amount of shifts. It's Monday AM, Monday PM till Sunday PM. Okay, 14 in total. What about the resources? Okay, so here we have the number of doctors in here, the number of doctors in here, and then the orange, the yellow, the green, and so on. This is for the AM, this is for the PM, okay? So here we have the shifts, okay? And then, as you can see here, I have several blue table, green table, yellow table, orange, several one-dimensional lookup tables, okay? The same I did the previous week with the shop simulation example. Then on every single table, there will be these numbers, okay? This is Monday AM, then it goes Monday PM, then Tuesday AM, Tuesday PM, then here, till the end, okay? So the main idea is that it's not these numbers and then these numbers. You take AM, PM, AM, PM, AM, PM, and so. Okay, so that's the idea for this lookup table, for every lookup table. Finally, I'm going to talk about the nurses. 2 nurses are in charge of the triage process. They both can do all triage tasks. One nurse is at full-time, the other one is at part-time on Fridays, Saturdays, and Sundays. As you can see, on Fridays, Saturday, and Sundays, here we had more doctors than the rest of the week, okay? So what about the patient's arrival? The patient's arrival is an exponential. It's an exponential distribution, probability density function. And these are the mean values, right? Remember, the previous week, I told you that instead of a random number by means of the exponential probability density function, you can use a uniform probability density function. Remember, minus the natural logarithm of the uniform distribution multiplied by the mean. And the mean, you can find the mean in here, okay? The mean is, as you may remember, 1 over lambda, the lambda parameter in an exponential probability density function, okay? But you can apply this depending on the shift, right? That's the idea. Depending on the shift, you can use different means. Here you are. And then you use the natural logarithm of a uniform probability density function, right? Well, what about the triage section? Obviously, the triage section needs a nurse, and after the triage section is finished, you are expected to release this nurse. Obviously, the nurse planning is placed in here and will depend on this information. But every patient needs a single nurse, as you can see here, right? What about the time it takes a nurse for the triage process? It's a uniform probability density function between 5 and 7 minutes. And remember, you must change the initial seat with or by means of the clock command in order to get a different initial seat for every simulation, right? That's the idea, remember. Obviously, this model will be run several times in order to get statistics. What about the patient classification, the triage results? Here, I use some idea I had used in the past, in the previous lecture. As you may remember, in the previous lecture, we had 2 different types of customers, remember? But here, we have 5 types of patients, 5 different severities of the illness of patients. So 5 different numbers will be assigned. So after the triage process is done, then you have a set attribute block, okay? And the attribute will be color. And how can you assign this color for an entity, for an incoming patient in this block, to this block? Well, you can do it like this. As you can see, this is the output port. This is the output port, fine. And here I have the different probability for every severity of the illness, okay? So you have a random number. This is a uniform random number, right? This uniform random number goes from 0 to 1. So that means that here you have the same probability to happen from 0 to 1. That's the main idea. So here I have a number from 0 to 1, right? So then here I check if this number is greater than 0.203. That's the probability for the highest severity of the illness, okay? Pay attention. By default, let's suppose that here I have, here in this signal, I have a 0.125, okay? Well, this number is smaller than the first probability, is smaller than this probability, smaller than this, smaller than this. So all of these outputs will be false because these blocks are compared to constant, okay, compared to constant. And how have I found these numbers? Well, 0.203 is the first probability for the first for grade number 1. Okay. Then here, this is the cumulative value of this probability and this probability, as you can see, 355, 355. What about this 0.434? Is the accumulation of these three probabilities. Then 0.837 is the cumulative value of these probabilities. So this way, if you had a number smaller than this probability, you should assign a patient color number 1. So that's severity number 1, because this is false, this is false, false, and false. So we have 4 zeros in here, a single 1 in here. So the resulting number of this sum, this is an add block, okay? Addition block, okay? So the resulting number in this addition block is only 1, because this is false, 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 and false, right? What about a number 0.231, right? This number is greater than 0.203, but smaller than all these numbers. So here we had a 1 in here. So number 2 should be assigned to this patient. So we have a patient of this level of severity, level 2, right? So the main idea is that here I have the same probability for every number to happen between 0 and 1. But then here I make the difference, because here I have the probability for every severity of the illness, right? That's the main idea. It's the same I did the previous week with the type of customer, okay? So, and here you can see that the color attribute is being assigned. Then what about the patient care? Well, let's keep in mind that you are only considering the first stage of the emergency stage, okay? So if some patient needs to go through a surgical intervention or something, it's not about the emergency stage, right? So what about the patient care depending on the severity of the illness? Well, if the severity is level 1, so the highest value, here we have between 15 and 13 minutes. It's a uniform probability density function, okay? So here, for every block, we have a uniform probability density function, right? That's the main idea. Well, so we have a longer time for the assistance of level 2. Remember, this is about traumatology and the like, right? So here we have a longer time than surgical interventions. Here, if someone needs surgery, is sent then directly to surgery. So the total time for the patient care of the highest level is not so long, okay? Because it doesn't depend on the emergency stage. Well, so the main idea, remember that you had red doctors, orange doctors, yellow doctors, green and blue doctors, right? The patients will be routed depending on the output switch. So every patient after the triage process is assigned a color. Depending on the color, it will be 1 red, remember, and 5 blue, the lowest value for the severity of the illness. So here you will acquire a green doctor, a blue doctor, yellow, orange, or red doctor. And obviously, after the process, you will release the corresponding doctor, right? What about the whole model? Well, first of all, the shifts in here, right? Then the resources. The resources will depend on the shift. So that's why the shift is feeding here all the lookup tables, right? Then what about the patient's arrival? Here we are, the patient's arrival, right? They depend on the time, right? On the shift. The triage section here, the color, as you can see here, sorry, here, the color is assigned at the end of the triage section, right? Here we have the triage section, the probability density function in here, the nurse acquire, and the nurse release. A color is assigned to every patient, and then depending on the color, the patients will be red, orange, yellow, green, or blue. Here, finally, I put displays in order to know how many patients of every severity of the illness, right? And finally, all of them go to a path combiner for an entity sync that will erase, that will delete these entities from the model, right? So for today's lab session, you are expected to build the whole model for the emergency stage, right? Now, for the second part, we will do the analysis on how the system is performing. Depending on the things we can observe, then we will give some ideas for the improvement of the system. And finally, you're expected to check these new ideas on the whole model. So let's go now to check about the performance of the system. So according to the information we have built the simulation model, and we will replicate the model several times in order to get some statistics. Here in the figure, I have shown you one of these several simulations. Okay, it's only an example. Obviously, this is not a histogram. Okay, so you're expected to get the information by means of histograms, because you will run the simulation several times. But here we have a specific example on what is happening in our system. Well, the main idea is that about nurses and red doctors, blue doctors, and orange doctors are all more or less between the 30-something% and the 60%, right? But clearly, green doctors, they have a heavy load of work, as you can see here. And on the other hand, we have yellow doctors that they have a small amount of work, right? So we have, on one hand, green doctors, heavy load of work, and this yellow doctors, light load of work. Obviously, because here we have the highest probability for the patients to have this type of illness, this level of illness, okay, for the severity of the illness. And on the other hand, we have the smallest value for the probability to happen this yellow illness, right? So we can think about how can we improve the system, right? Well, the main idea is that, for example, we could hire new green doctors, right? In order to make this green line to be lower and lower and lower, and to have the green line more or less here in between, right? But instead of hiring new resources, we could, for example, rearrange the actual assignment of doctors, because this, the severity of this illness are neighbors, as you can see here, and we could, for example, share doctors between two different neighbor areas, right? That's the idea. So the solution, or my proposal that I want you to check, to work with, is to share doctors between these two different areas, right? So first of all, I want you to build the whole model according to the basic information you have on the class notes, right? That are uploaded in the virtual campus, right? Once you have the whole model, then you check the behavior and check that it's something similar to this scope you have on the screen, right? Then what I want you to share doctors between areas, or in other words, to make these two-level patients either for the yellow line or the green line, right? This way. As you can see here, I have severity, level 1 severity, okay? Level 2 severity, level 3, level 4, and level 5, right? Nothing to do about red, orange, or blue. I'm talking about green and yellow, right? In here. Then, first of all, the green and yellow patients are mixed in the same path, as you can see here, by means of a path combiner, right? So they will be gathered together, mixed in this path combiner. And then they will be again outputted by means of this switch. But this switch will not be based on the same criterion like this switch. This switch is based on color. Remember, on the attribute color. Color 1, 2, 3, 4, 5. But this switch will switch by means of this criterion, round robin. Round robin or equiprobable. You can try both, right? The main idea is that these two entity output ports will be assigned, so the patients will be assigned to this port according to these different switching criterions, right? Different from the attribute criterion, because now here you can send yellow patients through this, or green patients through this, yellow patients through this output, or green patients through this output, right? That's the idea. And remember the difference. Equiprobable means that this block in here, this output, has the same probability than this output, right? So the 50% of patients will be sent through this, and the other 50 will be sent through this. And the round robin, remember, one patient goes through this, the next patient will go through the second output. the third patient through the first, the fourth through the second, and so on, round robin, right? And here you can see the before situation and the after. This is the before, remember, high level of work for the green doctors, low level of work for the yellow doctors. But now, can you see the green and yellow doctors in here? They are in the middle of the total of the general load of work for every doctors and nurses, right? That's the idea. So with this improvement, you have no need to hire new staff, right? New doctors, but you have rearranged the resources you have, right? And with only this new proposal, we have improved. This is only a single example, right? But you are expected to get the information by means of statistics, right? By means of histograms. That's the idea. Well, so the improvement of the system at the end will be the following. Here, remember, after you have acquired yellow and green doctors, you do all the assistance process, right? And after the assistance process, obviously you release yellow doctor and green doctor, the same you did before with red, orange, and blue, right? But then, here you have the numbers with the total number of patients that have been assisted with every, by means of every level of illness for every doctor, right? So as you can see here, numbers are quite similar than before, right? And as you can see here, half the numbers are yellow and half the numbers are green. Can you see that this is the same number because of the same probability or the round robin situation? The round robin criterion, right? Then finally, you combine all the patients in here in order to switch again by means of color, in order to count all the patients depending on the color, right? So this way we can check the total number, the ratio of the total number of every color, right, related to the total number of patients. So that's why here I calculate the percentage for every patient to happen, right? Here I count all the red patients, all the orange patients, the yellow, the greens, and the blues. I count all of them, I sum, I add, I do the addition for all these numbers, and I divide by this addition all the single numbers for every color, right? So this way I get the percentages. These are the result for a simulation, right? As you can see, this is the percentage of red patients. That is the same number, more or less, than the probability. This is the total number of patients in orange color, and it's quite similar to this 15%. This 7.8, 7.9%. That's the idea. Well, at the end, if you round this number, 7.9. Here, 40.3, 41.1 is quite similar. And finally, 16 and 17, right? You cannot do this by counting these numbers. Why? Because here in the yellow line, you have both yellow and green patients. And here on the green line, you have both yellow and green patients. That's why I'm expected to do this final stage in order to count and check that the percentages of patients are the same, than I have configured initially in the model, right? So the general view of the improvement of the system is, remember, the shifts, the resources, okay, nurses and doctors, the incoming of patients, the triage section, the color assignment, depending on the color, and be careful. Here I mix green and yellow patients. Green and yellow are assisted either by yellow or green lines, so no worries about that. And finally, I split patients depending on the color in order to get the statistics.